Hello everyone and welcome to day 2 of applications of derivatives. Today we're going to look at optimizing any certain function, which in this terms is going to be in terms of a context. But if we think about finding the maximum or minimum, which is what optimizing is, how did we do that with any sort of function? If I gave you y equals x squared and I said find the minimum value, what did you do? Well, you took the derivative, you set it equal to 0, and then you plugged in to find that minimum value. That's all this is. All optimizing is taking the derivative and setting it equal to 0. Now, the difficult part with it is actually finding the equations. So I'm going to try to walk you through with how to find the equations. You're going to pause it. You're going to see if you got the right answer, and then we're going to move on. I'll probably talk a little bit about it. But read the question and let me know, and pause it. So here we've got this fence that's 2,400 feet. And of course it was nice that we have a straight river. And so we're given a few things. Now one of the things I like to do is always write down our limitations. And so we have our limitations. Well, what do we know L has to be? L has to be greater than 0. And what does W have to be? Well, W also has to be greater than 0. So I always write those down. I know it doesn't matter with this if it's, we're not going to get an answer outside of these limitations. The one other thing that we also have to look at here is if the width or the length, whichever one it is more than, we'll call it the length. I don't know why I have L on the side, but I do, and we'll stick with it. But if the length is more than 1,200, 12 and 12, can W exist? And the answer is no, because it's 2,400. So we also know that L has to be less than 1,200, or else you wouldn't have a rectangle. So we're looking for a couple of things here. We're looking for the largest area. So what are we trying to maximize? We're trying to maximize the area, which means we're going to be taking the derivative of the area. So we got to make sure that that's what we're taking the derivative of. In this case, the derivative is L times W. Well, that's great, but how am I going to take the derivative when I have 3 variables? I have A, L, and W. We know we can do implicit differentiation, which I know you guys love so much, but you can't do implicit differentiation and solve for something when you have 3 variables. So this is going to be the goal, is to get this in terms of 2 variables. That's going to be the goal. So that's what we're trying to maximize. What are we given? Well, we're given what? We know that we have 2,400 feet of fence. So we're given that the perimeter, which we know is 2L plus W, we know that's 2,400 equals that. Okay. Well, what's nice about this? Well, which one is by itself? The W is. So let's solve for W. And, oh, how nice is this? We know what W is. What are we going to do with it? We're going to plug it into the area function. If we plug it into the area function, A equals L times 2,400 minus 2L. Now, what do we have? We only have 2 variables. And can you take the derivative of this? And the answer is yes. So we now have our area function. It's in terms of only 1 variable. And so now that we have the function, let's take the derivative. A prime equals 2,400 minus 4L. What are we going to do with that? Let me just note that this is dA over dL, in case you want to have perfect notation, taking the derivative with respect to the length. And so we're going to take A prime, set it equal to 0, which gives us that L equals 600. And so all that's telling us that the area is maximized when L equals 600. So again, I know this doesn't make sense here, and I get it. I just want to show you that when we have our limitations, I don't know why I just put test to it. When we have our limitations, we need to test. And test A of 0 a of 600 and a of 1200. Why are we testing these? And I know it doesn't necessarily make sense because we're not equal to, and so we don't actually have to test them, but it's in a good habit of testing these. And when you plug the 600 back into this equation right here, we're going to get 720,000 feet squared. And you just maximized it. Now, let's remember, it asks what are the dimensions. This is not the dimensions, this is just the maximum area this is the maximum area that we found. So our answer over here is 600 is our L, so length equals 600. How do we find our width? Well, we can find width by plugging back into it. Remember that we have this. This is 600 if we want to plug back in. And so we know that our width is 1200, and we should add our labels in. Okay? So we just found our dimensions. Dimensions 600 by 1200. So all it was, to recap, we draw everything out, we write our limitations. What are we trying to maximize? What are we given? Try to get this in terms of two variables. So we solved for W, we plugged in, took the derivative, set equal to 0, solved it, if need be, to test. In this case, that wasn't necessary, and then find the dimensions. Pause that if you need to and review that. In this case, let you pause it to read it. We have a cylindrical can. Cylindrical can is made to hold 1 liter of oil. Now, in class we're going to talk about this. We will not talk about it now. But just so you know that this is 1,000 centimeters cubed. And we'll talk about that in class. But that is something that we're going to have to use later on. So, a formula that you're going to need to know, area of a cylinder, is 2 pi r squared plus 2 pi rh. Are you going to need to memorize that? Because I know that's what everyone's going to ask me. No, you do not need to memorize that one. It will be given to you. And we also know that the volume is pi r squared h. Now, what are we looking for? The dimensions that will minimize the cost to manufacture the metal can. So, let's think about it. We're trying to find the dimensions that will minimize the cost of the metal. So what? Well, this is actually the surface area. If we're looking to minimize it, we need to find the minimum amount of metal we're going to use, which is the surface area. So this is what we're trying to minimize. So let's think about it. This is in terms of R and H and the surface area, so we got to solve for one of them. Well, which one do you want to solve for? Well, we know volume is 1,000 centimeters cubed. And so I think it's easiest to solve for H. You could solve for R and have a square root in there, and that's fine. There's nothing wrong with that, but I'm going to solve for H here. And then now that I've solved for H, this can go right there. So SA equals 2 pi r squared plus 2 pi r times H. Well, we know H is 1,000 over pi r. Hey, and look at this. The pi and pi cancel. You've got to start to see this, and that's a squared. R divided by r squared. Well, r divided by r squared is just r. So we do want to make sure that you can see canceling out. 2 times 1,000 is 2,000 divided by r. So that's what surface area is. Now, what are we trying to minimize? We're trying to minimize this. We're in terms of two variables. Remember, pi is not a variable, it's a constant. SA and r. So let's take the derivative. The derivative of it, or again, if you want to think of it in terms of dSA over dr, which is 4 pi r minus 2,000 over r squared. How did I get that? Remember this, just really 2,000 r to the negative 1. Bring down the negative 1, you get negative 2,000 to the negative second. When you subtract 1, we're going to get r squared. Set that equal to 0. Okay, if we set that equal to 0, we're going to get 2,000 over r squared equals 4 pi r. And if you solve for r, you will get the 4th root of 500 divided by the 4th root of pi. You can write it as the 4th root of 500 over pi. That is what r is. Now, if you need to solve, because it does ask for the dimensions, r does equal that, h then equals 1,000 over, if we look back up here, what h is right there, pi times, well, r, which is 4th root of 500 over pi, all squared. And I do want to, we can leave it, I wouldn't have minded if we left it as the square root of 500 over pi. I will show you in class if we want to. This does equal 2r, and I'm running out of room here, but h does equal 2r if you plug back in, and we'll look at that in class later on. I did forget to do the limitations, and just remember that limitations, r has to be greater than 0 and h has to be greater than 0. So there are the dimensions. The height is always going to be double the radius. I wouldn't have minded if you left it like that. I will show you again how we got that, but that's what you get. So those are the dimensions to minimize the cost of a metal can that can hold 1,000 or 1 liter or 1,000 centimeters cubed. Okay, so I do have a joke here. What do you call a group of unorganized cats? A catastrophe. Oh, isn't that a corny joke? Anyways, I thought I would at least lighten the mood a little. So one of the last problems I want to look at, and again pause it to read it. So you're given a box and we're going to cut out corners. We're going to cut out corners, and if you think about it, if we cut out corners, you can lift those sides up on either side. If we lift them up, you create the box. So the question is, we've got to cut out squares. Well, squares, which is nice, is they're both all x's. So we're cutting this part out so you can flip these boxes up, or flip the sides up, excuse me. So what do we have here? Well, we're looking for how large the squares be to hold as much as possible. This is what we were trying to maximize. We're trying to maximize the volume. Okay? Well, what do we know? We know that this is a 20 by 25 inch sheet. So what do we have here now? Well, if I take away these x's, or these squares, isn't that an x? And that an x? So my width, I'll call that my width and my length. My width is now 20 minus 2x, and my length is 25 minus 2x. These 2x's are the boxes that got taken, the squares that got taken away. So we have volume to equal L. Well, let's look at our height. Our height is the x, so we're going to make h equal x also. Notice that they're all in terms of x now. We're going to substitute in. And so that's our volume. I'm going to pause it here and do the workout. So a few things here. One, I've got the limitations. I'm not good at that. X is greater than 0. We also know that x here has to be less than 10. Because if it's greater than 10, we won't have a width. So x is less than 10. Here's the work to do it. If we take the volume, set it equal to 0, I did this by plugging it in the calculator. Please just plug in calculator. Do not actually do it out, or you can use a quadratic formula. Notice that this right here is 11 is greater than 10. We can cross that out. So we're left with this. You're going to plug it back in, and so the squares need to be 3.681 inches to get a maximum volume of 820.528. next problems continued on the next video.